Welcome to this last day, the workshop. Our first speaker for this session is Professor Peter Binev, Department of Mathematics, University of South Carolina. And his research interests include adaptive numerical methods for PDEs, nonlinear approximation theory, uncertainty quantification, and data processing. And the title of his talk is State Estimation in Reduced Modeling.
Thank you. I want to thank the organizers for the nice workshop and the opportunity to present. I have a lot of collaborators for this talk. So Albert Cohen, Wolfgang Dahmen, Ronald DeVore, Guergana Petrova, Przemyslav Wojtaszczyk. And the presentation is based on these two papers, which I'll not put in the next slides, and also supported by NSF. When talking about state estimation, at least I think about solving a differential equation. So if we have some differential equation, that means we have a differential operator L of xi. It's parameter dependent, and xi is a high dimensional set. Usually we assume it is infinite dimensional, because if we want to input some function there as a parameter, then we have to use infinite number of parameters to explain it. And so the basic problem is given some measurements which are finite number and usually expensive to get. So that means m should be relatively small number. Oops. So we want to find a solution u in some manifold, which is actually this is solution manifold, which is a set in U, such that the solutions U xi is a solution for some parameter which is acceptable. We assume that it is a compact set because in all the investigations that is critical for finding a solution. And we also assume that Lj are linear functional, and especially it's important property that they should be in the dual space of U, because otherwise the formulation will not be correctly posed. We usually achieve the solutions via Galerkin or Petrov-Galerkin discretization, and it could result in a very high dimensional space VH. And of course, if we work with VH, we have to restrict the manifold only for the solution from this finite element space. So the minimization problem, this is actually not a minimization problem, because there are plenty of solutions for this, because we have finite number of measurements. So we can make this zero. However, to fix the solution, we usually add some regularization term. So that is the usual way to get a state estimation. Here I'll talk about something else. And this something else is how to do the regularization in a different way, namely by reducing the dimension of the space in which we are looking for a solution. This is mainly because in most of the cases the regularization term is artificial, and it actually can change the problem in a direction we don't want to go. And the other, of course, if we work with a sparse space, if we have the Vn is small dimensional, that means we would be able faster to calculate the solution, and that's why we want to find some some good subspace Vn, which actually is good for most of the solutions. So at the beginning it seems almost impossible to do that, because we have this infinite dimensional compact set, and we want to approximate it via an n-dimensional linear space. However, in most practical problems it seems that this is the case. We can do it in a lot of problems, so we want to investigate whether we can find such an n-dimensional space, and the distance between the manifold and this space we denote by epsilon n. Of course, epsilon n is bigger than 0, but we hope that it's also small. So the reduced basis problem actually was phrased in many papers, but we are using this one from Madhepatera and Rinici. We consider the solution manifold, which is the solution of some differential equation, usually maybe something else, and we want to compute offline several solutions for different values of this parameter, and to consider Vn as a span of this n basic functions. So then we can introduce the orthogonal projection of this Vn and consider that sigma n is the maximum of the difference between when u is in M. So this is our epsilon n, and then we can do that offline, because actually finding such u's is a difficult job, and then online solve a very small Galerkin problem only with n elements and find the solution of the system. This should be F here in this place. So, but yeah. So how to find the reduced basis? First, the ideal algorithm is to apply a greedy procedure, which means to solve each time a one-dimensional problem of finding the furthest element of the manifold from the current state. So at the beginning, we of course start with the 0 point, and then find the element which has the largest norm from mu, and then we from M, and then we consider the end for the next step. We find the element which is furthest away from the previous n-dimensional space, and continue. This is usually not realizable, because finding the furthest element requires a lot of computations. So we want to do some feasible variant, which is called weak greedy algorithm. What is the property there? Instead of finding the maximal, the element which has the maximal distance, we want to find the element which is within gamma from that maximal distance, where gamma is the number between 0 and 1. Of course, if gamma equals 1, this is the best possible element, and that is the pure greedy algorithm. But in the weak greedy, we usually take gamma 1/2 or something. And but in finite elements, the good thing about solving differential equations is if we use the Galerkin approximation, for example, we have a residual based estimates, and the residual is very easy to calculate, and based on that we will know the error within two constants, C2, small c2 and capital C2, and which means that we don't have to calculate the actual error. We just need to calculate what is the residual error, and based on that we can actually achieve this this inequality, so that the distance is larger gamma. So in order to quantify the approximation, we need to define something which gives us the best possible subspace. So we have the space of functions, which is infinite dimensional. So and we have a manifold in it, and we want to approximate it with finite dimensional hyperplane, and actually hyperspace in this case. And we, based on the fact that we consider all possible n-dimensional hyperplanes and want to see which one has the smallest distance, and denote this smallest distance by sigma n. These are called linear Kolmogorov widths, and we can consider the bound sigma n from above from any. Obviously our result sigma n, which was on this artificial from this algorithm, would be bigger than this number, but we want to see whether we can find such a number. The other problem is that when I formulated the algorithm, I said that we are taking elements from the manifold. So the question is whether forming this n-dimensional space, for forming this, it would be good to take any n-dimensional space, only ones which are actually generated by the manifold. So if we use such spaces, then we want to know whether this new type of width can be compared to dn, and actually it turns out that it is possible, and then we pay only with the constant n for that, and this is optimal constant, because there are counterexamples which show that this width is could be bigger than n minus 1 times dn of the manifold. Okay, so let me explain with a picture what is applying the widths against greedy. So when, say, we want to approximate with one-dimensional space, this manifold, which is the blue line here, we want to use the best element, while in our greedy procedure we'll choose some element which has the worst error, which doesn't mean that it is the one which best approximates the linear space defined by it, best approximates the manifold. Then in the greedy procedure, the bad thing is that we have to keep that element, although maybe choosing two other elements like here the green points, we could find a better approximation, while here we're restricted only to the same sequence of elements. So the greedy basis seems not to be that optimal, and actually the first results there show that it has really bad constant here. The constant is 2 to the n, and actually when we started to prove, we thought to work on the problem, we thought, okay, we can improve. This is 2 to the n, it is ridiculously large. Turned out that we cannot do that, because there is a counterexample. We could find a set F for which the greedy algorithm will give us a constant which is at least 2 to the n. So that's why we had to find something else. So in most of the cases, however, the convergence is much faster, so that's good. But if it is not, then what we should do, and this is also only for the pure greedy case, and what can we do if we're in more practical situation where gamma is less than 1. Then we consider that. I'm not going to say anything about the proof. It's kind of tricky. We use a slow growth, but we consider the following setup. We say, okay, let's have that our Kolmogorov-Weights have certain rate of convergence, and let's see whether the greedy algorithm maintain this same rate of convergence. So in polynomial, if the rates are polynomial, that means n to the negative alpha, where alpha is some positive number, then we should have the same for the for our greedy procedure, except for some constant c here, which is not very bad, considering that it actually inflates n by a factor of 4 for that purposes. So the same results we receive for sub-exponential rates when we have this e to the negative a times n to the beta, where beta is number between 0 and 1. I want to remind you that for beta equals 1, we already have the result, which is from the standard results with the constant 2 to the n. So that is, these are the interesting cases. We were not able to prove that at the beginning, but later on, a subset of the authors, they actually modified the proof to prove that it's possible to have the same rate beta in both exponential cases. What that means? That means that the greedy procedure is very good in finding the optimal approximation with n-dimensional space, which actually have consequences, which means, okay, we don't know if we apply the procedure, we'll be receiving something good, but in case we really have that, we find the approximation that would be nearly optimal one. So what else is important? It is important also to consider what is the practical situation, because in the process of finding the reduced basis, we of course will have numerical errors, and we want to see whether we have robustness. That means if we have that the solution is slightly different from the one which we should have received based on the numerical errors, what will happen with the result? It turns out that nothing bad would happen, so we'll have in the polynomial rates the same result with, of course, we have the maximum between this numerical error and the rate, with a constant which depends both on alpha, which is the rate, and gamma, which is the weak greedy constant. And we can prove similar results for exponential rates. That means it's numerically feasible algorithm, and it can be applied. So I just want to refer for, I suppose that these results inspired some filmmakers to make the Wall Street movie, and this is considered the most inspirational actually speech in a movie, which says that greed is good, and that is actually what we did. So what we want to do now is to do the state estimation, of course. And when doing the state estimation, we want to consider a multispace setup. So we have our parameter-dependent PDE, and we have our solution manifold. We have some variational formulation which helps us finding a reduced basis, and now we have the elements U0, U1, and so on, and they define the spaces V1 to Vn. We also include the V0, which is just the 0 point. And we have some epsilons, which tells us how far away is the approximation of the dimensional space from the manifold, and so we actually have that instead of working with the manifold itself, we replace it with some cylinders around these n-dimensional spaces, which has the radius epsilon n. And now we want to use some data and to have the state estimation. What is the data? The data, I said these are linear functionals, but they shouldn't be any linear functionals. They should be linear functional from u prime. Say, for example, you can consider differential equation and say, okay, we know that we want this differential equation to have values u1 in the point x1, u2 in the point x2, and so on. However, these are point evaluation functionals, and eventually if u is a very nice L2 space, then the point evaluations are not linear functionals in L2. So that's why we have to consider something. We have to fix that Lj are exactly in the dual space u prime, and these are continuous linear functionals over u. So how can we do that for point evaluation? Of course, we can consider integration over a small region around the point and consider that to be the point. So the interpretation of data is important. And another thing which is important is that we have to have this property because that helps us actually consider the geometric problem and to consider pure geometric properties instead of consider the functional spaces in their full generality. So we'll consider a Hilbert space, although a lot of results can be extended, maybe not perfectly, but in a Banach space. And in this case, we can use the Ritz representers of these functionals. And having the Ritz representers, that means we can define a space of these Ritz representers, and we can consider the space W. And practically what we have the space Vn, which is our approximation, the space W. These are two finite dimensional spaces, and practically we can work in the union of this space. So that we work with finite dimensional space. So, and from now on, actually the data would be considered as a point in this finite dimensional space. And I want to point out that actually there are some problems in computation if depending on how good is the basis Wj. I want to emphasize that in most of the cases Wj are not orthogonal vectors, and because of that we could have that changing from this basis to orthogonal basis will be done with a matrix which has very bad condition number. But we ignore this problem because this is kind of numerical problem, and we'll consider only W, and we'll consider D not as the data Dj, but as a point of this space W. So what that means, so we have the space W, we have a point D in it, and we want to find a solution which satisfies these data points. That means the solution would be in D plus W perp. This is the space, this infinite dimensional space, which is perpendicular to W. So in a sense, if we have our manifold here, this one, and we have our approximation Vn, we want to have we have for our solution, it is within some distance epsilon n from Vn, and we know that it projects on a point in W. And the state estimation is practically having this point and having this space here to find the best compromise, to find a point which has the same data, and it is not too far from Vn. By the way, from here you probably can see that the intersection of this d plus W and the cylinder would be an ellipsoid. Actually, this is ellipsoidal hypercylinder, but that's something you probably can imagine what that is. So the thing is, so we have a Hilbert space set up. We have our goal is to find a solution which have the same data, and the data is given via some functionals which have their representers in U, and we have the measurement space, and the data is considered as a point in this measurement space. We have the orthogonal complement of it. We look for a solution. We know that the solution should be element of this hyperplane, and the reduced modeling is giving us some space Vn, and we know that the solution is within epsilon n from it. And we want to find the approximation that is close to Vn and to this space. So how to find that? In this paper here from Matteo Patera Panentiano, which Olga talked about yesterday, they do the following procedure. They find the arc mean of the problem D minus the projection of V to W. So I probably should come from here. So we have this space V. It projects somewhere here. So we can consider the projection and to find the point which is closest to our data from that. Returning back, that will be our V star. And then from this point V star, we will want to find the closest to it from the space. So we have a couple, U star and V star, which are actually, if you see two lines in 3D which don't intersect, and these are kind of the closest points from each of the two lines. However, this is in high-dimensional spaces, but it is the same thing. So what is critical? The critical is this quantity beta, which is the in sup of the two quantities V and W. This can be considered as the angle between the spaces. It's not exactly the angle, but it is close to that. And then in this paper, they prove this property, which we want to explain actually further. So we actually want to consider, so according to Matteo Patera and the others' paper, they have this formulation for the solution U star. We want to consider slightly differently. We want to consider it as sum of two quantities. One quantity is the data D, and the other one is something which is lifted from D to the space W perp. Because you remember we have that the solution should be of D plus W perp, and we want to find a point in W perp, actually this shift where U star should be. So how to find this? So this is some mapping which we call lifting, and we want to represent this. This is f of d, this is the lifting operator, and we actually prove that this considered completely nonlinear operator, but we prove that the optimal operator is actually linear, and we want to see how to find this fd. So that's the picture. This is actually the what I said. This is the hyperellipsoid here where the solution could be, and we want to find the closest point, which is the closest point between this line and this line, and this is V star and this is U star here. So the idea of lifting actually goes to the splitting in the space into W and the space Vn between W and W perp. So we can, because this covers the whole space U, we can consider each element of V has the portion in W and the portion in W perp, and based on that, we want to actually consider how the mapping from one to the other and define this lifting operator. And now we want this lifting operator to be optimal. In order to consider optimal, we should consider optimal recovery problem, which was defined many years ago from Micheli and Rivlin. So what is optimal? That means that for each data point D, it recovers the solution AD, so that is the algorithm, and it is optimal if for each solution we can have this estimate, where this C is the constant, which is typical for the algorithm, and of course depend on the data D. So if we, the question whether we can find such an operator, and we can consider further, we can consider instance optimal with respect to the whole space, not only for the individual data point, and see what is happening there. So what is given a space S? Here we practically define our subspaces. These are the spaces of if we consider this to be our manifold, which is D plus the W perp, then we can formulate similar quantities there. So in one space algorithm, which was considered with Madel-Patera, that was we actually were able to prove that it's instance optimal, and the constants of optimality is 1 over this quantity beta, and we call the constant mu. Between that, this is, as I said, this is kind of 1 over the cosine of the angle between the spaces, and the theorem practically says that whenever we have that, we can prove that the radius of the solution space is within the radius of it is approximated by this number, and in fact it's a very interesting phenomenon that actually this number improves the further this line D plus W perp and our space V and R, the better the estimate is, because we have here we subtract the square of that. We simply and it's kind of natural if we want to we have that our solution Vn is within epsilon from the solution manifold, and we already know that the solution we are looking for the state estimation, we have that it is already at least a distant some distance from it, this quantity, then we'll have a better approximation of where it can be. Because keep in mind that we could have several solutions, and this KD is the set of all possible solutions, so we want to find actually the center of that set to guarantee the better estimate. So, and in optimal recovering, we actually have that it's optimal with respect, so the general optimal recovery algorithm is actually achieved by a linear algorithm. This is exactly the one defined by Madej and Patera, and also this algorithm is optimal for recovering of in a more general sense, in a sense when we have the D is we don't consider one data point D, but consider all possible data points. And in this case, we also can say that this algorithm would be optimal recovery for the set. So now I want to say what we can achieve additionally if we consider all the n spaces. And in fact, we have several ellipsoids, which graphically I represent like that, and we know that our solution is inside of each ellipsoid. So if we consider the intersection of all ellipsoids, of course we have a better determination of what the solution is, and we want to design actually an algorithm which does that. It's a bit complicated, but it's not that much. So what is important in an analysis of these spaces, it's that we have an n-dimensional space. At most n-dimensional, we have this is j-dimensional space because we consider different spaces, and then we have our space W, which have n dimensions, and we could find an orthonormal basis in both of them in such a way that actually each vector corresponds to the basis vector from one corresponds to the basis vector of the other, and in fact that is received through the singular value decomposition of cross-Gramian, and we can find bases which have these nice properties. That means that this bases are orthogonal. We have this property between the two bases with the same indices. The others are 0, and we also have this special property for the projection of Vn over W perp. And based on that, we can actually receive some expression of how we can calculate and find the solution as the intersection of the cones defined of the ellipsoids defined through these formulas. And as I said, this also shows that we can subtract something, I mean, to reduce the solution and find a better estimate. So for this one, we actually have some theoretical estimates for that, and the theoretical estimates are based on the following observation. Because these ellipsoids, we have the biggest intersection if we align them to be centered at the same point. And what we do, we actually estimate the radius of the intersection based on the what that would be if we intersect all of them. And when doing that, we actually have an estimate which is actually, this is the picture. So this is usually the situation, but if we align them all at the same place, we can receive an estimate for the radius which would be varied for all of the cases, because in that case the radius would be smaller. Of course, it would be better to have an estimate there, but it's kind of hard to get it. And then this is actually the theorem which says that what is the radius of that? It has a constant 2 here. It is the minimum of all these constants mu, which are defined somewhere else. Okay? And thank you very much.
Question from the audience?
It's a small one. At the beginning you mentioned that you do this in the Hilbert space,
Yeah.
but you could generalize this to Banach spaces. But
Yeah.
everything that you showed depends heavily on perpendicularity, on orthogonality. So
Yes, but that actually can be, so you don't need to have orthogonality, you have to have a description of the space you receive, and this description could be done in a different way. So that's why we can do something. Okay, not all the results are possible, but the considerations are based on the description of the space in which we should have the solution.
So in the beginning, you showed an optimization problem using reduced models in order to solve optimization problems that are very common nowadays.
Yeah.
So, and there was also some kind of regularization term.
Yeah.
What do you use in order to solve this problem? Do we have any specific regularization terms?
Our regularization actually comes through reducing the dimension of the basis.
Yeah.
So practically, this can be considered a regularization term. Instead of imposing some conditions which are unnatural for the problem, we simply say, okay, if we are able to approximate this manifold through a very low dimensional space, instead of using the finite element space of very high dimension, we just want to go to the reduced basis, and then, because we have dimension n which is less than the dimension of the data space, so n is less or equal to m, and that means we can find unique solution in this case.
So what you can see is typically 2 or also an H1 regularization term, but it is okay. Second question about your gamma in your greedy, maybe I miss it. Is there, how do you choose it, or should it be an issue of optimization?
I probably have to go to show you how. This is actually we choose it smaller than that, but let me show that. I think it was.
Gamma is the quotient between the upper bound of
here.
the residual estimator and the lower bound.
Here.
Okay.
This is.
That's your residual estimator. An efficient and reliable is residual estimator. And the condition of that estimator, that's the gamma.
Yeah, here.
Yeah. Okay. Yeah.
This is the ratio. And of course, we can do it a little bit smaller because if we have to account for numerical errors, so in the computations, we usually should reduce it a little bit smaller, but it works with any gamma. So.
Yeah.
But you do not have to know the gamma for that algorithm.
Yeah,
You
because
only
the algorithm is
that gamma
optimal regardless.
exists, and then you are sure to be optimal. That's the thing. But you don't have to know it. You only have to know it exists.
Joseph, first question from
Yes, you talked about the situation where the greedy algorithm is not good, explodes like 2 to the power n. Could you give an intuition of the set f of compact sets for which it appears?
When it is larger than we prove actually that regardless of whether this explodes or not.
So you said there exists a compact set such that no?
Okay, I know that it's in the paper actually, but no. Okay,
there's a difference between the direct estimation of sigma n against dn for every n. This theorem covers only the rate. Suppose you have the following. Your dn goes like that.
I think he has something to
Suppose your dn goes like that.
Oh.
Could be have a very irregular decay. Its rate is this. Okay? And what this theorem proves is that the sigma n attains that rate. But in between sigma n and dn, there could be, for every single n, a big distance.
Okay.
Okay? But if you are in a situation where the dn are actually also close to their rate, then you have a direct comparison. But generally you cannot have that. And the result says that there could be gaps like this, but there is no gap between the rate. So the rate and an instant optimal comparison is different.
Okay.
It's weaker result than for each n.
Okay, let me just give you an alternative answer, because I thought you asked for that. So, I thought that he asked for whether we can have the greedy algorithm is 2 to the n times it's in the paper, the example. It's,
Okay.
However, the example we give there, it depends on n. So it's for the particular n.
Does this.
What exactly Wolfgang showed that we were not able to find something which consistently is away by 2 to the n. It should be something like this, coming down and then keeping the rate. And that's exactly the example we give.
So the people use all subspaces of a particular dimension in statistics as well, and they have n is a kind of sparsity. Sometimes statistics use S. I always wondered why people don't use the word Grassmannian manifold, because all subspaces of a particular dimension. That's a nice manifold. Maybe there's some theory about Grass manifold. I mean, people in algebra use Grassmannian manifold all the time to do stuff. Is there anything to do with that Grassmannian theory which could be used here? And I speak to statisticians as well, because they have what sparsity condition.
Probably. Maybe Wolfgang can say.
Potentially you could think of making use of it because that manifold has a certain smoothness.
Yes, exactly.
And when a manifold has a certain smoothness, you can imagine of doing descent type optimization procedures on that.
With D6 and everything
Exactly.
on the
And
Grassmannian.
when you search for an optimal space, that could be helpful. But I don't know of any instance where, in this context, that has been used. It is being heavily used in the theory of low rank and these hierarchical tensor
Sure.
formats.
Where there's a lot of algebraics in that field.
Yes, but not here, because you are searching in such a universe of possible n-dimensional spaces that you are very inclined to do something practical like a greedy method, which goes stepwise,
Very
and then
true.
you don't use directly the...
Well, let's all work on Grassmannian.
Okay.
Thanks again, Professor Binev.
Thank you.